Mr. Phil. All right, Mr. Phil sent me his 2KD Desktop Classic, which is in really good shape on the outside. And it looks pretty good on the inside, too. He said he's having some problems with getting the tuning right on it. I said, well, let me take a look at it. So, before I got too carried away, I just popped off the top plate. And the first thing my eyes went to was this. That's your whole high voltage section. This is your rectifying section right here. It's pretty important that these are locked down just for safety reasons and also to have heat dissipation. But so I've had to take this whole back sub-assembly apart. I don't know where the hardware for these have gone, Phil, but I know the guy that you said you took it to supposedly did some stuff to it, and then he did some other stuff and then pushed some shmoo on it and got out his magic pixie dust. But if he sent this back to you and you tried to run this like this, you're lucky you're not dead. So I'm going to fix that. And then sitting here looking at it, I was kind of screwing around with the tunes portion of the box here. And I can't help but notice, let's see if we can get it to bind up a little bit. I had this all re-indexed back to 0. Anyhow, here it goes. This thing's slipping. We sit here and we look at the drive section of it, or we'll bring it down to the end of it. Look at that. It's not moving anymore. It was doing it in the middle. So how that affects you is now that you're overclocked on the front, it's displaying 190 versus what it should be at 0. You see how the traveling arm here, little carrier wheel that's in there, it's just spinning. So we're gonna fix that too. Fix that too, and then we're going to flip it over and we're going to take a look at the bottom of it. So Phil, give me a little bit. I'm going to repair all of this and make it right. I'm going to put some more heat compound on the back of these bridge rectifiers. This is a diode string that is submerged. It's got basically a 10A 10A diode that's in here that's submerged in epoxy. But that's not the actual part number, you guys, but it's just a small 10 amp diode. There might be 2 in there between each one of those posts. But, yeah. We're going to slap some more heat compound on there, and then we're going to mount this thing back up. So, get that squared away. We'll get this re-indexed, and we'll get it so it spins smoothly and travels smoothly. And then we're going to go look at the bottom side and see what we get. And then we're going to throw some 3500Zs in here after we do some other preliminary volt testing. Now, I wonder how much loss we have in that cable. It is wired for 220 though, so we're going to take a look at that. I did notice that there is this very interesting splice that's in the middle, which feels like it's butt spliced together, which is a fire hazard. So I'll probably end up having to cut this all apart and repair this. And from what I can tell by the cable, it's been twisted multiple times. So we'll see what we get when we get into that. So, anywho, yeah. Mr. Phil, it's your time to turn and burn, buddy. We'll be back. So, Mr. P, I'm going to tell you this much. So we got this all ripped apart, Budrow, and we were sitting here looking at this bar, and this sits just like so on the back of the amp. And then your bridge rectifiers bolt to that, which are very flat and smooth. And I couldn't help but notice that the heatsink compound was not making good, even, uniform contact with this. And when I went to smear new shmoo on this bar, which acts as basically a heatsink for this, your high volt bridges, when they drilled this, they never deburred the holes, or somebody else has tried to hog this out in the past. There's a nice, big, tall lip of burr right there on this piece of angle bud, which, because these are flat, is going to hold the bridge off the bar. So we cleaned off all the old heatsink compound, the white jism, And by the way, say hi to everybody in Facebook land. They're looking down there watching us on a live feed at the moment. We're going to go and we're going to deburr all these holes, and we're going to start over and make it look all pretty for you and make it so it works right. But the only thing that was directly making contact with the metal was here at the eyelet points on the bridges where these holes are at. But we're going to fix that here. So give me just a minute, Mr. P. We'll get back to you, buddy. All right, Mr. P. We've gone and we've chamfed back the holes. And we took the lip right off of it, the nice big hairy burr. So now these bridges are going to be able to sit flat, and you're going to get way better heat dissipation, and it should work better than new. Okay, I'm going to recream this, and I'm going to put it all back together, and I'll come back with the next step. All right, Phil. When you sent me the Henry here, you said that you were having problems getting it to tune. So remember, a good operating amplifier has to have a good input tune before it can have a good output operation standards. And what I mean by that is that the input tune needs to be perfect for the maximum amount of input power to make its way to the tube. But when you get good input power, usually the output circuitry is a lot easier to get settled down. So what we're going to do is we're going to run through the bands real quick. Right now we're currently on 80 meters.
Give yourself to the dark side.
Yes, give yourself to the dark side. Sorry, my phone's going to go off throughout this. I'm trying to shoot this in the middle of the day. So up here on our analyzer, this is our spectrum analyzer. It is also a spectrum analyzer. This is my network analyzer. But the bandwidth plan from here to here, so we're looking across a huge diversity of frequency at the moment. If we look up here, where the little red indicator's at, that's going to tell you where the red cursor's at. Okay, so we're looking in this corner over here, 7 megahertz, all the way down to 0.0 or 0.250 megahertz. So now what we have here is the input resonant chart for this entire frequency band with the amp in the 80 meter position, and we're currently looking at the input circuitry. Now I'm not going to show you how to do this on video or how to set this up, even though everybody knows how to do this. I'm not going to cover it. Right now we're doing what they call emulated load. Okay, and for you to achieve emulated load, you got to bypass the relays, and then you have to have the tubes in the socket, and then you have to add some other magic SMU to the inside of the amp deck. All tubes have an emulated operation mode, and what that means is with the amplifier off and then not charged, by the use of a small couple components, you can go in and create the environment that the tube is going to produce when it's in its state of operation. So what we've done is we scroll through the frequency here. Let's see, it's the top portion of 80 meters is like 4. What we've done here is what I'm showing you on the dip. And this is the beauty thing about most tube amplifiers, and the reason that you don't need to have band cut, high pass and low pass filters or a band filtering board, is because the circuitry inherently lends itself to being very notched. Like I said, my phone's not going to stop ringing. It never stops ringing all day. That's the reason I normally shoot these things at night. Okay, here is the bottom end of the 80 meter band. Here's the top end of the 80 meter band. And here is the center of the 80 meter band. So we can see at the very top end we're starting to get close to not being in an acceptable resonance. Towards the lower end of the band, you're pretty spot on. But right in the middle, where most people do most of their talking, as I sit here and I scroll the red cursor down, you can see that correlates to an SWR ratio. And you can see your capacitance and inductance and everything. At the dead center of the band, you have a 1.020. Okay? And we're going to shoot for that as we move through. Now, when we get into the upper frequencies, like towards 11 and 10 meters, the frequency response is going to become very flat. And so then you tune for the lowest flat resonance point that you can get for optimization of the entire band. Okay? But right now, as this stands, without doing some serious modification to the internal operations of this thing, that's about as resonant as you're going to get for 80 meters, and that's about as choice as you're going to get it set up. Now we can do a couple little things on the inside to spread this out and make it a little bit flatter response. But this is the way it is from Henry. I went in last night and had to do some tweaking on the little slug to bring the center dip, or otherwise the center resonance point, into alignment for 80 meters. So at this point, I'm not showing you guys how to actually set this up. I'm just explaining to you how to read the meter. So frequency edge to frequency edge, the center cursor, which is our center line, 3.650. Our two cursor points, which are represented up here, and they're addressed standing wave ratios. Okay? So we're going to go ahead and we're going to flick the switch. We're going to go on up over to 40 meters now. So now we just flipped the band switch to 40 meters, but now we need to adjust the meter. So we're going to take center, and we're going to type in 4, or no, pardon me. Oh man, it's been a minute since I took my ham test, you guys, and I never ever use it. 7.000. Okay, so the bottom end of the ham band is 7.000. All the way to 7.300. Now, if you can see here, very clearly represented, we got the dip as close to center as we can get for right in the middle of the ham band. And if you think about it, since we're looking at this, we're looking from 3.600 to about 10. And us kids get to play on about that much bandwidth. Hell, the wire's almost thicker than the bandwidth they give you to use. When I mean they, I mean Uncle Charlie and the Good Time Gang. Okay, so let's go ahead and jump on up to 20 meters. So we're going to take our center and we're going to change that to 14.00000 enter. What's going on here? Let's get our field set up here. So we're going to go from 14 flat to 14.350. See, now nothing's set in stone here. I set this up last night and had it beautifully tuned out, I thought. I mean, that's still way within an acceptable resonance. Let me see if I can get in here and tweak that slug a little bit more and get that the center dip, this dip, bring it more over towards our actual resonance. Which I think I remember last night when I set this up at 3 o'clock in the morning, I was running out of adjustment here. Nope. It's moving over there slow. Let's come down a little bit. See if I can tweak it out a little bit more. I think, if memory serves me though, we got it pretty as resonant as it's going to get. And still, that's pretty acceptable. I mean, your radio's not going to freak out and say that you're showing it a fake you know, giving it a high SWR. You're not going to have to turn on your antenna tuner between the radio and the amplifier or nothing, but really we're shooting for, you know, titties here. Oh, it's such a pain. There's such a small amount of space. I had to take my non-conductive tool. There, I'm finally back in the friggin' spot. Had to cut it down to modify it into the small amount of adjustment space they give this thing. Yeah, it's starting to go back up again. Yep, I had it adjusted down as low as it could go when we started. I mean, still a 1.2 and a 1.4 is not out of tolerance. And I played with a couple other things. I added a few capacitors and did a couple other things in here to bring this down from where it was at. Yeah, I'm totally out of adjustment now. And what I mean by adjustment is I can't enter in any more turns. There's a coil and a ferrite slug that's in here. Okay, we'll back it back out. I just ran it back in. I'll back this back out again. We'll go for the lowest that we can achieve. It's about as good as we're going to get it. So let's go ahead and we're going to move on. We're going to go to 15 meters, which, let's see, is 21 through 21.4. So we're going to go over here and we're going to do center 21.000. And that's well within acceptable range. So 1.2. And that's between these two cursor points. That's all the bandwidth that we get. It's depressing once you get your head wrapped around it. Okay, we're going to go ahead and go to the 10 meter selection, which is almost wide open and flat. So we're all the way down on 21 megahertz. We're nowhere near the 10 meter band. So now, me being a dork and knowing this guy, we'll go tune in for the Super Bowl. Now, as you can see, the center line is 6. Okay. Let's take our little red cursor and we're going to cruise on up here towards the amateur band. And you can see that dip is pretty much center on the amateur band. This little dip right here. It's dead center in the middle of the amateur band, but it'll work fine out towards an 11 and 12 meters. No problem. 12 meters is about in here. 11 meters is right in here. But that's it. The input tune on this amplifier is pristine. And I mean in really, really good shape. It wasn't that out of whack. I just went in and did some really fine adjustments on it. And I mean really fine adjustments to it. Nothing to get excited about. So on that note, let me reset and redo our emulated load and capacitance on the top for our output. And we'll show you the output in reverse. As in we're going to look at it with the analyzer in reverse. And you guys, you got to understand, I do this with Heathkits, I do this with Drakes, I do this with everything that comes in here. I've just never bothered to slow down and shoot the video of it. So I was showing it on Facebook the other night. I didn't show exactly what I was doing. I just showed the meter and explained to everybody what I was doing, and everyone went, wow, that's so cool. So I thought I'd come forward and show you guys. Anywho, give me just a minute. I got to reset, change some stuff around, and then we'll get back at it. Okay, buddy, I wanted to show you the input side of your deck here real quick. We've gone and bypassed the output relay. So that's the reason this relay is missing. because I got to solder to the pins, and I don't like exposing these delicate little gems to any kind of stress whatsoever because they're delicate. The primary problem with a lot of these, the Henrys, is that they'll stop keying. And what happens over time is this board that makes up the backer for this relay gets soft. Or somebody goes in here and they pull the relay out and they're not very delicate with it and they just rip the relay out. These little tabs, see the little turn tab here? And these two little turn tabs down here on the bottom? That's what holds the relay body together. So what happens is that relay body gets a little bit stretched, those posts get a little bit stretched, and the guy goes to step on a pedal and nothing happens, okay? And so then they'll smack the amp, or then they get frustrated with the amp. Come to find out, what causes that is the coil that activates the solenoid motor in here, or creates the little electrical field, the magnetic field that pulls the actual solenoid arm down that causes these to close. Just by moving it, by stretching it just a hair out of width, it doesn't have a strong enough field to actually suck that bar down. So it won't allow it to go into transmit mode. Yeah, food for thought. So I tell everybody that owns one of these to go out and get themselves, hold on a second, to go out and get themselves a replacement set of these relays. Very handy just to have sitting in the drawer. Anyhow, I'll be back. And the hits just keep on coming. Okay, Mr. Paul, so what we got here is we're now looking at your output side. And as I move the roller inductor around, so here, watch. So in here is a little carrier arm. See that thing moving around? This little transfer wheel. If you watch it real close, you'll see there are times where it doesn't touch the wheel. Like right about there, the wheel doesn't touch the blade of the conductor. So what happens is we get these weird little resonant dips. Right now we're down on 80 meters, so the wheel's making contact right now. But if I move it just a quarter of an inch, now it's not making contact. I got to cover up the amp deck section because I don't want to show you guys how I emulated load. I'm not going to show that to the general public. Here, I'll do it while it's up here on the top side. Maybe you guys will be able to see it. So right now it's not making contact, and you can see the nut on that thing isn't turning. And there, now it's making contact again, not turning, not turning, still not turning. Now it's making contact again. Not turning. So what I got to do is I got to take this armature apart over here, and I got to retorque it because somebody's gone in there and they've pressed on it too hard at one point or another with their finger, and they bent it away. So it's barely making contact, which is bad because this is the high voltage, or not high voltage, but the high watt side. And then, Paul, when I flipped it back over, I couldn't help but notice we got another problem going on here. This should be rock solid. So the mounting hardware, which is over here in the corner, down here in the back, is either come loose or come completely off. So this is only being held in by one screw. So I got to take the whole flipping thing apart and repair that. So first I'm going to get this right, so we can get this to settle down. Look at it, it's just sitting there jumping all over the place. There is your tuning issues on your output side. The input side was not that bad, but the output side, see, this should stay very steady. This dip should be very steady as I move the roller inductor around, and it is not. See how it jumps? I should be able to very smoothly take this and walk it back and forth with its resonance. Okay, let's get to taking a bunch of little screws apart. Whoop-a-doo. All right, so I ended up taking the roller inductor out, and I think I covered in the last segment why. Now, no matter where I put the traveling wheel that goes through the center of the roller inductor as this thing moves back and forth, is making contact on only half of the inductor wheel. So it'd make contact and break contact, make contact, break contact, make contact, break contact. And it wasn't tracking right. Well, I recognized there was a bigger problem afoot than just bending the bar back. Because if we look down in here, we can see there's a bunch of scratch and scuff marks down there about where my thumb is at. Well, that was from these little handcrafted parts that are sitting here. And they were dragging here on this plate. And they're also dragging here on the front plate. So I went through the hassle. Now, I did this live, you guys, on Facebook. I took this apart live. And the customer that owns this amplifier, I did that intentionally so he could watch me take this apart live, because he was having a hard time understanding what I was talking about. So I explained all of it, and I showed that when this whole thing was assembled, you could take that wheel, the little contact wheel, and just by rotating the coil up and down, the wheel would just go. It wasn't touching anything. I don't know how or why, but these are the spring. This is the armature arm, okay? And then attached to the armature arm is the center conductor bar, which runs down the middle of the coil. And then you've got these two little pieces of metal that act like springs. I don't know what they're made of, though, that attach to the inductor wheel and the inductor wheel arm. Well, here's our problem. No matter how I would go about indexing these two arms, which are totally adjustable, because the craftsmanship of the little springs is so poor, you can see that the holes are off center to each other. See that? They're actually even, but the ones that make contact with the bar are uneven. So instead of sitting nice and straight, it's actually sitting at an angle, which causes this wheel to bind. I did this live, and I have to go back and I have to reshoot and talk about what I did and why I took it apart for you guys, the YouTube viewer, that are going to watch this video downline. So now what I get to do is I get to find some hardened copper like this, and I have to fab up two new pieces to fit in there and make them that they're even. There's too much distance there. So no matter what way I would have adjusted this, that wheel would have never uniformly traveled up and down that coil. Never. So let me get on to making some parts, and I'll be back with another little bit. Fun, right? And people wonder why it takes me so long to get anything done, because it might look good from afar, and then I get up close, and now guess what? It's far from good. So we'll get her figured out. I'll be back. Nice and smooth contact now. The camera's kind of at an angle. You can see where that bar is perfectly even now. So I took some new pieces of nickel-plated, silver-plated copper that is hardened and cut them out. So now it's got nice smooth armature clearance over here and really good clearance over here. See that? And then I didn't put a pretension in them, otherwise I didn't put a bend in it. I put it in there straight and then I reassembled it. Now this coil should be able to flex, which these things are notoriously famous for rattling inside the amplifier. And it wasn't until I had it apart that I realized, I don't know if you guys can see that or not, somebody has gone and hot glued all these, the top and the bottom of the coils in place to keep it from chattering when the amp's running. But I think, as far as this little bit of the thing is concerned, this problem has been repaired. I think. So, all right, let's put it back in the amp. I gotta shoot this in reverse. I was already packing up to be done with this thing, and thought, oh shoot, I forgot about all my YouTube fans. I did this once on Facebook, but this is in high definition. I know the customer will appreciate me making the storyline straight. So right now we're tuning in the 10 meter position, okay? Now, we got the roller inductor back in, and we got that all working. So we're gonna run through all the bands real fast, because I gotta go barbecue the family dinner. But over here, we're looking all the way up to 30 megahertz to 23 megahertz over here. So this is a full frequency dip, okay? But it's real time. That's the difference. It's the advantage of owning a network analyzer and not a grid dip meter. Grid dip meter will give you the same information, at least some of the new ones. Like the A100, and I guess Mother effing Junk finally produced a meter that was worth a damn that does this. But okay, so what we're looking at is that little green cursor that's right there, and the green cursor is indicated by marker number 2, 27.025, 1.044, which if I wanted to spend the next 3 minutes of my life, 4 minutes of my life tweaking with the tune and load knob, I can get that to drop to like 1.27, but this is what I wanted to show you. So that's the middle of the CB band, right? So let's move on up into the ham bands. We can move that resonance anywhere we want. So if the amplifier is tuned properly, the output portion of the amplifier doesn't care exactly where it's tuned to. That's 28.78722 megahertz with a 1.034 resonance. Okay? Now the reason that we got to go through all the different bands, let's go ahead and we'll move the band switch on to 15 megahertz. Is that there's a great big series of doorknobs that kick in and kick out. And we're looking at this, if you bypass the relay, we're looking back into the amplifier on the amp deck section of the tube or the amp. And learning how to emulate load, understanding how to read that in a schematic is very key. So as I'm adjusting the tune and the load, so when you got your mic key, click audio, and you're trying to peak the box out, or you're trying to get as much output power out of the amplifier as you can, this represents the tunable field that the amplifier can produce power, and you're trying to bring the tunable sections of the box to where it's within resonance. And by slowly jogging the tube back and forth with no wild motions. And by the way, this is the hardest you can be on a tube. There is a 1.012 standing wave reflect. Otherwise, it's perfectly in resonance. Now, the data that I can pull from this is I'd know what my marker numbers are on the front, the actual key indicators that are on the front of the box. The problem is most of this information that you retrieve from this, or your MFJ, or your Atlas, or your Telwave, or whatever it is that you want to hook up to the coax connector to get this kind of data, you can do just regular, put it on a, you can do a Telwave and do the 1.02 thing. You can look at that till you go batty-eyed. This makes it really easy for you to visualize it. Okay, the reason I went after this most advanced network analyzer that I could find, and this isn't the most advanced, but this is also a spectrum analyzer and a signal generator. It's an IFR unit. It's a tone generator. It's a freak counter. It's a signal loss generator. It's also, you can use it in a closed loop system. So I can use this thing to generate RF coming from the unit, put it in place of the device, tell this unit what the output emulated load field would be, and then look at the entire circuit from the device's point of view. Either be a transistor, a MOSFET, a tube, and look at it all the way out to the coax connector and be able to look at all my different impedance pumps. It's also an OTDR and a TDR, which is a time to default and an overall time to default. There's a lot of different things that this one unit does. That, and it's potable because I can take it and put it in my hand. I loved it so much that I bought two. I got one that I keep locked away that's on the bench, and the other one that I take with me when I go on road trips because I want to go look at everybody's stuff. So if you ever see me walking by you in a break and I got a little black box in my hand with a little tiny antenna on it, I'm field mapping your vehicle. And from that field map that this thing allows me to look at, I can Smith chart your entire signal platform. Just saying. This is an amazing device. It's truly worth, I believe, the $1,800 that they asked for this unit. I think they probably have come down in price. I think they're $12 or $14 now. But when I bought this, it was $1,800. Worth every penny. It kicked open a bunch of doors and allowed me to take a bunch of huge clunky equipment. You know, like I have an IFR unit here, but it's huge. This thing I can literally put in my cargo pocket and walk around with it. I can change the refresh rate and make it read full time. Okay, enough bragging about this little piece of equipment. But this is by far one of the most advanced pieces of equipment I have here, as far as all the different jobs it does, packed into one unit. Let's go ahead and we're going to drop on down to 20 meters here. Let's add some induction. Whoop, here it comes, nice and smooth. Look at that. Oh. Add a little bit of capacitance. Now we're going to take out some induction. Take it out, take it out, take it out. Nice and smoothly. We're going to add some more capacitance. Oh, overshot it, so now I got to add a little bit of induction. On our roller inductor we just rebuilt. Okay, 1.062. Obviously this thing is going to tune perfectly for 20. Let's go talk about 40. So we're going to add some more induction. Here it comes, here it comes, here it comes. Capacitance to it, overshot it, so let's redip it back the other direction, add a little bit more induction to it, and add a little bit more capacitance, a little bit more induction to it, take away a little bit of capacitance, keep taking it away, move the roller inductor one more time. 1.06 again. So the last two digits of this are gobbledygook. Like I said, the data that we're getting from this is just a rough reference. Because once you go and introduce the high voltage of the RF field to the tuning device, where this is only producing 500 milliwatts, so otherwise 1/2 of 1 watt, okay, that this thing is producing, versus the 3,000 watts peak power, or roughly 1 kW, give or take, 1.4 kW RMS power, average power, that this unit can produce, there's vastly different voltages. And as we all know, as you apply more voltage to a circuit device or anything, it's what? Its resistance changes, okay? So therefore its inductance is going to change, the capacitance is going to change. So this gets you a rough number of where to head. Outside of that, man, got to put a foot pedal down and start talking on it like a man. All right, here, center 3.50, enter. Oh, 80 meters. Spin this some more. Nice and smooth. Add some capacitance here. Dip it back, add some more induction. little bit more capacitance. Okay, we're gonna need more induction. There it is. 1.3 or 1.032. The thing I like about tubes is that they're very inherently clean. And what I mean by that is the circuitry that surrounds the tube, for the most part, keeps the resonant circuit. So to make the circuit resonant, the window that it's only resonant on is very narrow. It's very, very, very narrow. Okay? So that means if there's any harmonics that are being produced in the device, mostly, that are off frequency here and off frequency here, they don't see a resonant circuit pathway, so they come back into the device as heat. It's kind of cool. If you adjust your input circuitry the same, you have a very, very inherently clean device, just because of the way that the circuitry tunes itself on the inside. That's why you'll see in most solid state boxes, because they set the actual circuitry that supports the solid state box up to be very broadbanded, you'll see in there a band selector board that has got a low or usually a high pass filter, a notch filter system that kicks in and engages for each one of the bands, and it's got what they call a high pass cut. So anything that's above in resonance is going to be cut, and everything that's going to be below is going to have a cut on it, which allows it to be a filter. A lot of guys don't like using them because it takes away the numbers on the watt meter, but then again, the numbers that you're seeing on the watt meter that you're not seeing are garbage, so it doesn't do you any good anyhow. Alright, so what we've proven to ourselves and to you, the YouTube user, if I haven't already bored the socks, underwear, and the panties clean off your person, is that this big beautiful thing, as far as a mechanical advantage goes, roller inductors, input tune, output tune, that kind of stuff, this thing is sound. It's taken me a day and a half to get to where it is electrically sound, to where I feel like I can move forward now and start doing a little bit of other testing on the high voltage side. So now it's time to start turning it on. I gotta go get my 220 volt variac, get that out, get that set up. Yep. As far as mechanical, this thing will work. Now it's all the electrical components around it to see if it's going to actually chooch. Okay, on to the next step. I have a small problem going on. Listen to this. Hear that? I'll do it again. Click. As soon as I bring that high voltage online, it's arcing someplace, but it's building all kinds of power at the moment. I've got this extra 120 millimeter fan on it because I don't have the chimneys for it. I told them to leave them at home, and I figured I'd just put a fan on top of it, and it's working fine. I was looking at it with a FLIR. So somewhere in this area over here, I've got something that is letting it leak to ground. I don't know if it's through the center of one of them bleeder resistors, but I gotta get that figured out before we go any further. Its building power works perfectly. I just had it on 80 meters doing like 1300 watts with only 80 watts of drive. Peak envelope power, of course. Thing works really well. But it arcing like that. Give me a minute, I'll figure it out. It's all fixed. I had back there in the high volt section, please know how far away I am. I had it leaking. The high volt section was bleeding over through one of the, there's screws that go down through the bleeders, and it was arcing over into one of those screws, and then it was jumping back to the inside of the resistor body, which was a pain to figure out. I had to take the face off, and then I had to pull the amp deck out, and then I had to slide the back of the amp out, and then I had to figure out where it was arcing and put the whole thing back together. It's not arcing. Woohoo! I got the whole thing back together now, you guys, and it's running like a Swiss watch. So let me show you. I'm going to show you on multiple bands, and we're going to cut away, and then we're going to hook it up and drive it like a CB'er and see what it does for power. I know that the ham community is like going to lose their friggin' mind, but it's the way the CB guys run them. I went through and I got everything running. Standby light works now again. High volt, operate. Everything runs perfectly now. Absolutely perfectly. I'd say that this is pretty equal to what it would be like if it came off the factory floor now. I replaced all the screws on the bottom side of this amp. All of them. They were all hoggered out, wallered out, and looked like poo. But this thing is a clean Henry, and it's in really good shape. So anyhow, let me put this thing on the tripod. We're going to switch over to the ICOM 706 Mark II-G, input bird meter. It's a 1,000 watt slug over there. I'll stick my hand back there. 1,000 watt slug back there, 1,000 watt slug in average, 5 watt slug in reverse, 50 watt slug in reverse between the ICOM 706 Mark II-G and the Henry. Okay, give me just a second. Okay. Last thing, Phil, that I did is I fixed your CW sideband switch on the front of the box, which is high-low. It was sitting there just spinning. That now all works. So you can see we're in the middle of the 80 meter band. Now, of course, we are on a dummy load and a sealed grounded system, so I don't have to worry about it going off into the outside atmosphere. So we don't have to worry about anybody freaking out about that. Remember, reflect going in, reflect coming back from the dummy load, average, peak power. We're on 80 meters. Show you drive, hello, 100 watts. Hello, 1,000 watts on sideband, no problem at all. Let's go over to AM. Hello. Just burying it. Hello. That's on half an amp. Pulling 500 mils of plate amperage. Perfect. So let's see here. It's going up to 40. As you can see, we're obviously in the middle of the 40 meter band again. So I made me some notes, which I'm going to send along with this thing. Let's turn this little dial here on the front. So it is real hard on an amplifier for you to sit here and tune it. And tune it. And tune it. About 109. So again, 100 watts. Let's see. Showing no pass-through power. Let's see if we got anything here. There it goes. Just nowhere close to being resonant, that's all. Okay. Turn this back around the other direction. down on low. Here it comes. Please note our input. Remember how much time I spent tuning that earlier on in the video? This hasn't moved. Because it doesn't matter what the output resonance is, the input circuit is going to tune to the inputs. The RF is going to go into the tube no matter what. That hasn't come up. And if you notice, 1,000 watts, that's on low. Let me flip it over to the sideband mode. Just nails it in the corner. Let's go over here to sideband. Let's see. We're above 30, so it's going to be lower. 3. Audio. That's it. So let's go on up to 20. Once again, we're in the middle of the 20 meter band. Bring this over to AM. Flip it down on low. Oh, let's see, 55. Turn the knob till it reads 55. Start about there. We're going to tune this for about 109. One water reflect. I gotta let the tubes cool off for a second. I've been standing on them for a minute. So let them cool down. I got the two bottom bells hot. See, you got the bells, the carbon bells. Yeah, two of them are hot. We're right at about 55, and on the load we're looking at about a 115. 118. Now we're on low. Let's hit the gas. And we'll go over and we'll run it in sideband. Perfect. Absolutely perfect. So go ahead and we'll go to 15. Once again, in the middle of the 15 meter mode. Take this down to low. Let's see, so now we're going for 38. I'm getting tired, you guys. It's been a long day and I still got a whole nother amp I gotta go work on yet. Input tune's still down at 0. I'm going to put this up on high now and hit the gas. Off the scale, just gone. Back to upper sideband. And it's pulling 700 mils worth of grid. Pardon me, 700 mils worth of plate amps. And the high voltage is dropping off when we do that to 2800 volts. So let's go to the happy band, 10 meter band. And it's going to be around 10 on the tune. about 109 again on the load. Oh, look at that. It's already on the funny band. It's about 900 watts with about 90 watts of drive, and that's on the CW or tune function. So we're going to click this over to sideband now. We're going to go to the high mode, and it's gone again. So audio runs like a rape monkey. So that's it. Let's bring this over here. Now what I'm doing is I'm tuning this. I'm constantly walking back and forth between the tune and the load. And what I'm looking for is an increase in power. And I'm tuning for my maximum amount of output power. Okay? So you're going to have your dead key, and that's when you step on a pedal. Audio. And as I'm bringing it into resonance, I'm adjusting the tune and the load to bring the dip, the resonant frequency dip. Remember when we looked at it on the flat chart on the network analyzer, and we're able to bring the resonance, the big valley back and forth in resonance? Well, you slowly bring this back. Tune and load, tune and load, tune and load. And like I said, for the 10-11 meter band, you're going to be about 11-12 over here on this indicated dial. And down here, you're going to be at 109. In that neighborhood. And that changes. But once you get it tuned up, just touch the knob and dip it. Just bring it back just a hair. Just scooch it. Boop. Dip it back. That's what everybody will say is dipping it. And you'll be really happy with the results. Okay. Look, guys, I got more work than I know what to do with. And I'm thinking about really narrowing back the new build side of the business because I got more repair work than I could ever possibly do. Of course, if I cut back on the week's worth of build time it takes to make new boxes, I can spend, like, I rebuilt this entire amp today. This is 1 amp done compared to where I would just been started on, let's say, building a 24 pill or something like that. I think I'm going to start focusing real heavily on HF gear and repair work. I've got a lot of projects over here, you guys. I've probably got another 12 SB220s sitting here, and I've got yet another Henry that's sitting over here, and it's a floor model that I got to figure out what's going on with it. If you've got one of these and it's not working, I'm your guy. Send it here. It's like I want to be the SB220 guy. Guess what? I am the SB220 guy. I got more SB220s here than I can even shake a stick at. I want to do these. I want to do Henrys and Drakes and SB220s. I want to make that my thing. I love the 3500 Z-Tube. It's a lot of fun. So we're gonna fade out here in a second, and then when we come back for the final portion of this video, finally we'll be done with it. We're gonna hit this with my 2-pill and the 2950, and let's see it make some power. Give me just a minute. Let me reset. This is the part where most amateur radio guys are just gonna want to reach up and hit stop. Look, I don't care. I want to work on everybody's box. I don't care if you're a ham guy. I don't care if you're a CB'er. It makes no difference to me. I live in a don't ask, don't tell, and even if you do tell, I don't care universe. I just want to keep the hobby going. That's not going to make sense to a lot of ham guys. I don't know why they don't want to share knowledge and they don't want to teach the way they used to about 20 years ago. I don't know why they're so judgmental. There's so few CB'ers left. And let's face it, guys, a lot of the HF community is dying. There's not a lot of people coming into the community, so we need to support each other and make it fun again. But I know this gentleman, and I have spoke with him on the phone, and he is going to run this thing this way. Now, it's got a 1 amp transformer in it. We're going to put about 800 mils worth of load on the power supply to achieve this. We're not going to overdrive into grids. We're not going to totally ruin the tubes. Now, if you stayed on the tubes to the point where they were so saturated like this, they are going to overheat. But because this has got a chimney system in it and a blower in it, this runs just like an SB220. You've seen me do this 100 times with the same set of tubes. I mean, literally 100 times with the same set of tubes. The only difference is there's about 300, 400 more plate bolts on the tube on the Henry. So let's get going. Let me show you what we got going on. Now, I have not changed the tune and the load, but these tubes will take up to 110, 120 watts worth of peak envelope power drive. Peak power, not average, peak power. And I get phone calls all the time. I didn't know you could drive an SB220. I didn't know you could drive a Henry like that. You sure can. They will take it with a smile on their face, and they will sing, and they go. You just can't be long-winded. You can't go and check into the whatever net. Key down. Hey, Bob. It's Kevin. Yeah, man, so today I got up with the wife, and then I went out and washed the car, and you can't do that. You got to fire down, use the thing, and then come out and let the tube lose the heat. If you want to stay that keyed up, back that plate voltage down, back that drive down, bring the output power down to about 1,000 watts, and the tubes will last you for a lifetime, and you can stay on them as long as you got enough air moving across them. That ain't what we're doing here. We're going for absolute max output power. So, first let me show you what I'm putting into it for drive. Now, this far scale is in 1,000 watts average, 5 watts in reverse, and then this one is the input reflect. Now, I know that's like a mile off. Don't worry, we're going to fix that here in a minute. We're going to peak up to about 300 watts of peak power. So we're going to put about 130, 140 peak watts into each tube. This is a 50 watt slug in reverse, and we're getting 3.5 watts of input reflect with 300 watts going in. That's perfect. It's perfect. Now let's scoot over here real quick. Now that meter on the left is average. The meter on the right is peak envelope power in 1,000 watt. Okay, we made that 1,000 watt just disappear. So now I've gone and I've hit the multiplier, so now full deflection on this meter is 2,000 watts. Gone again, just off the chart. So now we're going to bring it down to the 5,000 watt mark, which 1,000, 2,000, 3,000, 4,000, 5,000 watts. And peak power on AM. There's 3 grand in peak, and it'll hold it. What I'm doing is I'm peaking it out. I'm over here and I'm playing with the load, and I'm going to go back and hit the tune. So about 800 bird on AM, and roughly about 3,100, 3,200 watts peak. SB220, I'm not happy with it until I see about 23, 2,400. On a Henry, I want to see 3,000, 3,100 watts. Period. With my little 2-pill hitting it. I'll do it again. BBI. Audio. We just seen about 900 bird out of this. Look. I love these amps, and I love working on this stuff. It's a lot of fun. Let me take the camera over one more time. Because there's going to be some guys that are going to freak out about this. Oh my god! Oh my god! Yep. Kind of scary, isn't it? Audio. About 800 mils is all we're pulling off the tubes. We're pulling off the power supply. Like I said, because this isn't like a SP220, which uses a voltage doubler and is on a 1 amp transformer, this is a true 1 amp transformer, but it's full bridge. So there's more room, there's more headroom. The transformer can put up with more punishment and produce more volts and more amps and not get as hot. Hello, audio. Hello, audio. Okay, maybe 850 mils. Hello, audio. Only 200 mils on a grid. I'm killing it too hard. So, guys, at the end of the day, it's another one saved. Like I said, I like working on Henrys. I like working on Heathkits. The problem is a lot of guys, they don't want to spend the money to send this thing up here to get it repaired. But I seriously doubt that the gentleman that owns this amplifier would have been able to do everything that I did for it today. And I poured a lot of love and time into it. Guys, I appreciate you all watching. I ain't gonna sit here and hold your hand any much longer. I appreciate you watching all the way to the end of the video if you did. On to the next one. I think the next ones are worth more. On that note, I'm going to say, gentlemen, be patient. There's so much more cool shit coming from the shop. I'll see you guys. Bye-bye. Well, one last thing, Phil. This extension cord, it goes to this amp. It's ridiculous. Where is it? Oh, yeah, right down in there in a corner. Right down there in the corner is where your old butt splice used to be. I went ahead and I pulled the splice thing together that your buddy put together for you. I took this out and I went ahead and I cut it, and I went ahead and soldered it and heat shrinked it and made it all perfect. So you get to keep your extension cable, but I'm going to throw that in the trash. Phil, you're all good, buddy. Gentlemen, my name is BBI. Without a shadow of a doubt, I am the biggest mud duck in Idaho. And I'll just build something bigger, because it's what I do. I appreciate y'all checking out the video. Got any questions, anything I can do for you, want to send me your Henry to get worked on, call that number right there. Talk to me first, and I'll get you squared away. Gentlemen, peace out. I got to go and edit the video. I'll see you. Bye-bye.